Hi everybody, this is a video showing you the uses and introduction to the mole concept. The mole concept is the most important calculation aspect of the entire 2-year A-level chemistry course. You will use the following relationships involving moles and substances, solids, liquids, gases, aqueous solutions throughout your entire chemistry career. The specification with regards to this particular topic is pretty detailed. First of all, formulae and equations. We'll have a look at writing formulae for ionic compounds and also recognizing some very important anions and cations that the exam board will expect you to know. How to make up balanced equations, and later on we'll also look at ionic equations as well. The main part of this video is the mole concept itself, and rather than going into the depth and detail of moles and the quantities and so on, more concerned with the actual use of moles when handling laboratory quantities and the significance of relating the contents of a balanced chemical equation to the actual quantities. More about that later on. And in a separate video, we'll have a little look at some applications of moles, uses of moles in some other areas of analysis. Okay, so to begin with, I've just shown you a periodic table copy. Of course, there are plenty of these. The ones I'm interested in this first piece are the non-metals, and especially the group that I've shaded in yellow. The ones shaded in yellow are non-metals which exist as diatomic molecules. That is, two atoms joined or bonded together with a covalent bond to produce a molecule. And so when these elements are referred to by their name, nitrogen, oxygen, fluorine, chlorine, bromine, and so on, you must know they exist as N2 or O2 or F2 and so on. There are two other nonmetals which are very different. These are phosphorus, which occurs as P4 molecules, and sulfur as S8 molecules. All the rest of the periodic table are predominantly, of course, metals, and their giant structures will have many, many atoms, far too many to number, so we just use the symbol for the element for everything else. So it's important you remember the hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine group, the ones in yellow, and the other two, phosphorus and sulfur. Well, of course, when we come to put ions together to form compounds, then we use positive ions and we use negative ions. These are formed when electrons are transferred from one atom to another. The elements which indulge in ionic bonding tend to be the extreme ends of the periodic table as we look at it, namely in the metals groups 1 and 2, that's columns 1 and 2, and the non-metals in columns 6 and 7. So for the reference to that, we're looking at the group of elements, the column in starting with hydrogen and lithium and sodium and so on, beryllium's column, and also the non-metal element columns starting with oxygen and with fluorine. Those tend to form ionic compounds. The elements on the left, the metals, will lose outer electrons, forming positive ions. The non-metals on the right will gain those electrons to form negative ions. And here's an example. In the example shown, sodium with a single outer electron will transfer that electron, losing it, becoming a positive ion, and the chlorine atom gaining it, becoming a Cl- ion. And once these ions are formed, their opposite charge, their electrostatically attraction to each other. So we call this opposite charge attraction electrostatic attraction. And that's what sticks the ions together. Well, as a general guide for you, column 1 elements form 1+ ions, column 2 elements form 2+ ions. And then column 3 all the way over to boron and aluminium, they form 3+ ions. The carbon group tend not to form ions, well, certainly not the top elements, but then we go backwards. The nitrogen group ions are 3 minus because they need to gain 3 to get a full outer shell like neon, for example. Group 6, the oxygen group, form 2 minus ions, and of course the halogens, group 7, 1 minus ions. There are some, in fact there's quite a few of these are more complicated ions. They're called molecular ions, or they used to be called radicals. These are ions which are made up from more than one non-metal atom, and you simply have to learn them. Hydroxide, nitrate, ammonium, sulfate and carbonate. You would be expected to be well aware of these and how to name them and write them. There are 2 other metal ions which the syllabus says you must know. These are zinc 2+ and silver 1+, Ag silver. Well, when it comes to writing formulae for ionic compounds, we must make sure that there is no overall charge. So however many positive and negative ions it takes, when we put these together, there must be no overall charge. Now, there are several ways of doing this, and I'm fairly sure you will be familiar with at least one of them. Firstly, what we call a cross-multiply method. Well, a very simple idea, if we put together the aluminium 3+ and the sulfate 2- ion, then fairly readily we would put 2 lots of aluminium, because that gives a total of 6+, and 3 lots of sulfate, because that gives a total of 6-. So when we put those 2 piles together, then the overall charge total is 0. So the formula would be Al2, little 2, SO4, 3. Notice the use of the brackets to keep the sulfate ion together and to separate that 4 and 3. We don't want 43 oxygens. Well, an alternative way of doing the same thing is what we call a factors method, and this one is my preferred way. For example, if we're combining copper 2+ and phosphate 3-, then simply by using the numbers, the charge numbers, 2 and 3 are both factors of 6. So very simply, how many 2's in 6? And of course the answer is 3. So I want 3 copper 2+. How many 3's in 6? Well, of course the answer is 2. So I want 2 PO4 3-. So very simply creating the formula. Similarly, Cu3 PO4 bracket twice. And a third example is a nice diagrammatic way. If you're stuck working them out other ways, then there is a simple diagram which basically gives the cation, the magnesium in this case, 2 positives, and the nitride ion, N3-. Well, of course, if we put just one of each ion together, the overall charge will still be -1. So if we put a second magnesium along with the 1 nitride, then the overall charge will be +1. There is only one way that we can make sure there is no overall charge, and that, of course, is to have 3 magnesiums, 6+, and 2 nitrides, 6-. So in any way we do this, then the principle is the same. We must have no overall charge. Okay, so the mole, symbol N, is the unit of chemical quantity, and moles relates to everything. It is extremely important. This particular slide should be etched on your memory. Moles allows us to convert and connect between any types of substances, aqueous solutions, solids, liquids, gases, with any other concentrations, volumes, or other measured amounts like mass and molar mass that we would use or measure in a lab. The most important relationship we're going to come across is the one between solids and pure liquids, not solutions. And this is this one. Moles, mass, and molar mass have that simple relationship. Moles equals mass divided by molar mass. For aqueous solutions, extremely useful in titrations and practical solution work. This relationship involves moles, but this time with concentration and volume. Now, in volumes, we must be using dm cubed. So this is cubic centimeters, of course, divided by 1,000. The concentration unit is moles per cubic decimeter. Please get used to them. They will be very familiar to you. Now, this is an unusual one. It's a bit of a contrived triangle. We don't tend to meet this a lot in practical work, but it is quite a useful one when we're asked to work out a number of particles. So number of atoms, number of molecules, number of ions, number of anything really. Well, the relationship is simply this. The number of particles is the number of moles times the Avogadro constant. This is the familiar 6.02 times 10 to the power 23. This is the number of particles in a mole. And so obviously we need this whenever we have a question asking to calculate the number of atoms, moles, molecules, ions, etc. The last relationship is a very restricted one, and this is the simple relationship we use for gases, but very specifically gases at room temperature and pressure. The very simple idea that 1 mole of any gas occupies 24 cubic decimeters or 24,000 cubic centimeters at room temperature and pressure. Room temperature, of course, is 25 degrees C, 298 Kelvin, and 100 kilopascals. That's the pressure, 1 atmosphere. So the 4 moles relationships you see on the screen will be extremely important to you. And the feature N is present in every single one of them. The power of these expressions is really, can't really emphasize how important it is to us. We're going to use these relationships throughout the course. Please learn them as soon as you can. Get used to them, be familiar with their units and so on. Okay, so the first of the triangles, moles, mass and molar mass. An example, this one very often used, a very simple connection and a very simple example, the way of using the equation to enable us to calculate the number of moles, for example, 23 grams of gold. Well, of course, that number of moles is simply the mass, 23 grams, divided by the molar mass of gold, 197. So the answer 0.12. And of course, you will need any 2 of the 3 components, then you can use the triangle. So you can use mass and moles or mass and molar mass, any 2, and you can find the missing 3rd one. Extremely useful. For solutions, then this one involves concentration and volume, and here's the relationship. Moles is equal to concentration times volume. The volume must be in dm cubed. You are often likely to have to change your volume units between cm cubed and dm cubed to use this triangle. And as a simple example, calculate a number of moles of 200 cubic centimeters of 0.35 mole cubic decimeter HCl. And a very simple calculation, of course, indeed. Notice we have to change the volume to dm cubed to enable us to use the triangle. Be prepared to alter this triangle again using moles, concentration and volume. So we will use this one a lot in year 2 as well, where we find the concentration from moles divided by volume or vice versa. The gas triangle, remember, is only available at RTP. Please watch out for room temperature and pressure. And the very simple way to use this, of course, is simply to calculate number of moles is the volume dm cubed divided by 24. And again, be prepared to rearrange and use the triangle accordingly, because it's quite a simple one. We only need the gas volume to be able to use this one at room temperature and pressure. Finally, of course, the number of particles. The Avogadro constant number is on your data sheet, so you don't need to remember it, but it is applicable to any types of particles. So the number of particles is the number of moles times the Avogadro constant. And of course, again, be prepared to use this relationship as it is very important. Not many questions on this, but we do get them.